Okay, good morning everyone. So we are continuing with chapter 4 today. So what have we learned so far? Let's do a little recap as usual. So kita dah belajar about KE, we learned about UG and also about UE. Then you're going like, apa benda KE, UG, UE ni? So KE is kinetic energy, UG is gravitational potential energy, and UE is your elastic potential energy. So U in general is potential energy, and you have two kinds, which is UG, which is the gravitational one, and also the elastic one. So gravitational is when you have an increase in height, or when you have a decrease in height. So that is related to your gravitational potential energy. And when you have a spring system and you extend it or you compress it, you are changing the length of the spring by x, right? You're changing the length. Therefore, that translates to your UE. It becomes your elastic potential energy. And then your kinetic energy, the typical equation that we all know is 1 over 2 mv squared, and UG is mgh, and UE is 1 over 2. Aduan, nak cakap apa-apa ke? Oh, tak ada. Okay. So, saya dengar ada bunyi tadi. Let me see the participants. Semua dah muted. Okay. Okay, never mind. So KE is 1 over 2 mv squared. This is velocity. So when we have a change in velocity, we have work done. Okay, and that can, work done can, oh sorry, kenapa ada delta W pula? We have work done when we have a change in kinetic energy ataupun when we have a change in velocity. In this equation, the only thing that can change is only your velocity. Your mass cannot change unless you're like a superhuman being, but you're not. So let's stick with changing the velocity. So KE final minus KE initial. When you have that change in kinetic energy, it becomes work done. And this is related to your this is also known as the work energy theorem. And this theorem is very important because sometimes it makes our life easier when we're calculating. Let's say you know that the total work done on this object is this much, and they're asking you, hey, what's the final velocity? So you can use this equation to do that. So work energy theorem. And sometimes they can ask you, what is work energy theorem? So you have to know what it means. Okay, and then for this guy, work is done when we have a change in UG. So any change in energy, it becomes work done, but we have to know what type of energy and change lah. So when we have a change in UG, we have work done. And for this equation, we can only change the H. Do not change the mass or do not change the G. During the exam, I had someone asking me, Doctor, can G become 5? No, G tak boleh bertukar. Korang, kalau G bertukar, habis kita porak-poranda kat dunia ni. So G tak berubah. Kalau kita cut surface of Earth, does not change, guys. Okay, so please stick to changing H only. So mg delta H. Waktu saya dapat soalan tu, saya panik. Saya tolong panik untuk korang. Ya Allah, macam mana G boleh bertukar pula ni? Okay, tapi baguslah. Semua orang pass, alhamdulillah. Okay, and then for UE, your K does not change. It's the property of the spring. So when you're extending it or you are compressing it, the material stays the same, right? The property of that material ataupun the property of that spring stays the same. So the only thing that you can change here is X. So your work done becomes change in UE, or it is 1 over 2 kx final squared 1 over 2 kx initial squared. So that is your equation for work done. Okay, so that is your recap lah for what we have learned so far. So now we're going to talk about energy transformation. So energy can be transformed from one form to another. So for example, you can have mechanical to mechanical. So mechanical yang kita belajar adalah kinetic, UG and UE. So UE can be converted ataupun transformed into UG, or KE, or KE can be transformed into UE or UG, vice versa lah. So potential energy can become kinetic, potential energy can become potential plus kinetic, mechanical can become electrical. So tapi kita tak tengok kat sini. And then other cases where we have nuclear that becomes mechanical and electrical. So you have the nuclear power plant. So that is how you get your energy lah from the nuclear reaction. Okay, so when you have a nuclear power plant, they transform the nuclear energy to become other types of energy yang selamat untuk kita pakai. Then for chemical energy, you can have it in electrical and also in mechanical. So chemical energy is like battery lah. You have that chemical reaction in the battery, it gives you electricity. And from the electricity, you put it in your toy car, and your toy car moves, so it becomes mechanical energy, right? It becomes motion, or KE, kinetic energy. So these are all the transformation of energy. And how is it possible to have this transformation? It is because of the conservation of energy. Wait, okay, this one. It is possible because of conservation of energy. So in an isolated system of objects interacting through conservative forces, only the total mechanical energy of the system remains constant. So for example, if you started with a E initial of 100 joules, your E final will also be 100 joules. So this part, it confuses people. So we're going to talk more on that. So let me go back to this sentence. What does it mean? In an isolated system, which means that it is shield from other sources yang tak berkenaan. Kiranya macam in physics, when we solve something, we are assuming cases that are isolated. Contohnya, saya tengah duduk sini and I ask you, hey, what is the, okay, this is gonna be hard example. Yeah, what is my, how do I see this? So let's say I have a car moving lah. Ya Allah, kenapa kasih macam ni? Okay, so I'm saying, hey, what's the kinetic energy of this car if the velocity is 10 meter per second? But in an isolated system, I wouldn't care if there are other cars that is going to make my car slow down. Contohnya ada car datang dari tempat lain kan. This is a car, by the way. Ada car datang tempat lain, and then the car says, this car A sees car B, so it has to slow down, right? So I'm not assuming that, I'm not taking that into assumption. I'm saying that this car is an isolated system. Bila dia berjalan with a velocity, it's not bothered by anything else. So that is what it means by isolated system. Other cases of isolated system would be macam when we're talking about pressure of susah lah nak bagi example macam ni. Sekejap. But you guys get it lah kot. When we're talking about the physics concept of a system, we're not taking consideration of benda-benda lain kat luar tu. So it makes our assumption easier. It makes us to solve this type of problems easier. So this is what it means by isolated system. So physics use that approach untuk approximate ataupun to solve things in general lah. Okay, so that's just like an introduction to isolated system. Okay, so when you have an isolated system of objects interacting through conservative forces. Conservative forces means that forces other than friction. So that is my simplest way to define it. Forces other than friction. Kenapa dia panggil selain pada friction? Sebab friction makes our system lose energy. Friction makes our system lose energy. So when we have an incline and this guy is dragging down, but at the same time it is being impeded by friction. Friction menyebabkan dia slow down. So actually friction is making this system lose energy. Dia slow down kan, when it becomes slow, the kinetic energy also becomes lower. So friction is actually our enemy ataupun it's a non-conservative force. So friction is non-conservative force. So other forces that we are going to talk about other than friction, it is known as conservative forces. For example, gravitational force, what else? Elastic force, forces macam tu reaction force, reaction force. So semua benda selain friction. adalah non-conservative. Semua forces selain friction adalah conservative. Friction is non-conservative forces. So you just have to remember this guy lah. Just remember friction is a non-conservative force and you're good to go. Kita nak padam. Okay, so let's talk about this one. So total initial energy is equal to total final energy. In this case, we have U plus K, U initial plus K initial equals to U final plus K final. So U in this case, it can be UG, it can be UE. So I can write it like this. It's I. Then if you have UG in the initial side, you will have UG in the final side as well. So it's not restricted to UG only. You can have UG plus UE plus K. Boleh. So it becomes complicated lagi. So this becomes equal. Okay, so you will have the same things on both sides. So if we're talking about UG and K, on the final side, you need to have the UG and K. If you're talking about all three together, then please put in all three together. Walaupun salah satu becomes a 0, just put it there. Okay, so that it balances the equation. This becomes I, final, final, final. Okay, this is final, final, this is I. Okay, so boleh ke kalau we're just going to talk about U equals to U? Yes, you can. You can just ignore K. Let's say memang tak bergerak benda tu. So you can say UG plus UE is equal to UG plus UE. So it works asalkan both sides are balanced. Okay. So in general, non-conservative forces may also be present. When we're talking about this guy, U plus K equals to U plus K, we are ignoring friction ataupun non-conservative energy. So, but in general, we know that friction is going to be there. It's our enemy. So in general, non-conservative may also be present force, such as friction. If non-conservative force are present, then some of the initial mechanical energy is lost due to the work done to overcome the non-conservative force. Like I mentioned to you before, if we have a box moving down an incline and we know that there is some friction acting on it, that we know that it is going to slow down due to the friction. Therefore, if let's say friction tak ada, if friction tak ada, KE is 100 joules. But when friction ada, my KE drops down to 80 joules. So I actually lost energy by 20 joules to overcome friction. So the work done by non-conservative force is going to be 20 joules. Okay. Okay, so I'm going to repeat myself. Initially, without friction, I say, oh, my kinetic energy of this system is 100 joules, so I'm happy about it. But suddenly, I put my box, they changed the situation where the incline becomes rough. So now my KE drops down because it has to sacrifice some energy to overcome friction. But where does that energy go? Remember, energy cannot be created nor destroyed. It has to go somewhere. If KE is losing 20 joules, where does it go? It has to go somewhere. That 20 joules goes to the non-conservative work done, which is the work done by friction. So if we are going to write this in terms of equation, how do I write? Okay, let me go here. So this is the equation when we have friction. So UI KI minus work done by non-conservative force. Remember when we had initial energy that was not bothered by friction. But now when we have friction, we have that minus sign. So our total energy drops down. So what happens? If I started with 100, now it becomes 80. Therefore, my E final also needs to become 80. Dia tak boleh jadi 100 dah. Tadi mula-mula EI equals to F, EF, 100 and 100. What is this? 100 equals to 100. But when we have friction, it drops down to 80. Walaupun EI ni 100, tapi dia tolak 20. So EF becomes 80. It is still balanced we need to make it balance. So tak boleh 100 tolak 20 tapi kat sini equals to 100. It doesn't work like that. So when we have a drop in energy, someone has to pay for it. Someone will become slower, someone will decrease in height, something will happen. Okay, so we are going to look at that. Okay, so this is the last part of chapter 4 before kita akan buat banyak-banyak example. So this is about power. So we talked about when we have change in energy, it becomes work done. But when work is expressed over time, it becomes power. So this is joules per second. This is the unit. So joules per second is power, or the unit that you are more familiar with is called watt. Okay, so joules per second is also watt. So it is the rate of work done. It is the rate of work done. When we're talking about rate, we know that it is going to be divided by time. So let's say the rate of hari ni saya punya brain is not working well. So the rate of work done is joules per second. Other forms is rate of displacement. Rate of displacement, what is that? X over t, which is velocity, ataupun rate of velocity. Rate of velocity is v over t, which you get a. When we're talking about rate in general means we divide something over time. So when I'm talking about the rate of work done, it is actually power, because work over time is equal to power. Okay, so other common units that we don't need to know, but I'm just going to tell you guys, it's horsepower, 1 HP. So when you see 1 HP, this is what it means. It is 746 watt. So horsepower is a form of power, tapi dia unit lain lah. Macam we have, when we have miles versus kilometer, we use kilometer. We don't really care about miles, but it's there. So horsepower is like that lah. Power, we know that it is watts, but another unit of it is horsepower. What did I say? Yeah, itulah power and horsepower. Kenapa lah nak pakai horse tu kan? Saya pun tak faham. Alright, so problem solving strategy. So 820, okay. Read and understand the question, visualize and sketch the situation. Of course, identify the forces acting on an object. So here we have to use chapter 3 punya skills. Then determine whether there is any non-conservative force. In our case, we are focusing on friction. Whenever they say the incline is rough, whenever they say it has friction, you know that there will be W and C in your equation. So locate the initial position and final position of the object. This is very important. Kita akan tengok kenapa. Because your MGH is affected by this, your UE is affected by this, they are affected by position, right? UE and UG. So this is very important to know your initial and final. Determine the potential energy and kinetic energy at both the initial and final. Determine the zero reference position for potential energy. For gravitational potential energy, the lowest level is the zero. So when we're talking about objects that are moving up, we take the ground level. Why am I labeling as G? We take the X equals to 0 down here as 0. Ataupun H equals to 0 kat sini. The bottom is our zero reference. And for elastic potential energy, the position when spring is unstretched, meaning the original state of the spring, is taken as the zero reference. So if you have a spring, if it stretches or if it compresses, this is your zero. This is your zero. So if it stretches, it becomes positive X. If it is compressed, it becomes negative X. Okay, so it's very important to know this. Your spring, when it is unstretched, is your zero position. Typically, we start at the end. Ambil kat ujung ni, that is your X equals to 0. When it is stretched to the right or to the left, it will become positive X. When it is compressed to the right or to the left, we typically say this is negative X, negative displacement. Untuk gravitational potential energy, when you are increasing the height, When you are increasing the height, it is positive h. When you are decreasing the height, it is negative h. We take the ground level as h equals to 0. That is our reference point. Okay. Okay, so apply the conservation of energy equation. We know this EI equals to EF, but when we have friction, it becomes EI minus WNC, non-conservative work done, equals to EF. Kalau value kat sini berkurang, your EF also will have to drop down. You don't have to care how. You just have to know that it needs to be balanced. Okay. So what if you wanted to put your WNC on the right hand side? Boleh ke tak boleh? Boleh So UI plus KI equals to UF plus KF. If you don't want to put this on your initial side, you can put it over here, but it becomes positive. Now let's talk about the EI equals to EF that we talked about earlier, where we had 100 joules and this was 100 joules. But when we had friction, I introduced friction, then the 100 joules becomes 100 minus 20, and this becomes 80. So this is EI minus WNC equals to 80. Now, I told you we can put the WNC on the right hand side. So if I want to put this WNC on the right hand side, it will become 100 equals to 80 plus 20. So balance lah kan? So when it is on the initial side, it is a negative. When it is on the right hand side ataupun final side, it becomes a positive. Allah, why do I like to write on the hujung-hujung? I don't understand. I don't understand myself. Okay, let me rewrite that. So EI plus minus WNC, no, plus WNC, no, it's minus. Minus WNC equals to EF. So this was 100 minus 20 equals to 80. But if we want to put the WNC on the right hand side, we can do that as well. So this becomes EI equals to EF plus WNC. So as you can see, it's 100, 80 plus 20. So it is still balanced. So my point here is that if you are putting this WNC on your initial side, it needs to become negative. If you put it in the final side, it needs to become positive. Which one is the best one to use? I don't know. It depends on the problem, but I usually like to use it on the initial side. So nanti kita akan tengok problems. Whichever way that works for you, just use it. Okay, you can use the negative or the positive. Substitute the known values and calculate the unknowns. WNC is equal to 0 when friction is not present. State your answer. Do not forget units. Okay. I'm gonna take like 3-minute break sebab saya penat cakap. So if you have any questions, you can ask me. So 8:30 saya akan sambung bercakap. You can look at this example while I'm resting my throat. So any questions? I need coffee. No questions, everyone's jam gila kan sebab saya cakap non-stop. Sabar. Memang macam tu awal-awal. Nanti nak buat example nanti, korang kena buat. Oh. So no question? Oh, I have one chat here. Awal-awal. Betul. And Friday pula tu kan. Ni pengorbanan kita. Amy dah start touching. Saya tak nak start touching, nanti saya sedih. Apa yang jatuh tu? Okay. No question then? Alright, so everyone's good. Kalau nak tengok YouTube doktor walaupun doktor ajar K19 boleh ke? Boleh lah, of course, it's open. You are always welcome to watch my YouTube. Nak tanya pun boleh. Kalau bosan-bosan rindu-rindu saya, tengoklah YouTube tu. Korang janganlah touching sangat. Nanti saya sedih tau. Saya sedih nanti susah jadinya. Nanti saya menangis sekarang. Okay. Apa tu? Haikal buat drama guys. Ya Haikal, it's okay. 8 minit je tak apa. My WhatsApp is available. If you need to talk to me about anything, you can talk to me. My YouTube is available. Web Science still ada walaupun Dr. Suzy yang handle. Web Science is still there. And soalan insyaAllah sama macam apa yang saya assign untuk kelas lain. Video saya okey ke tak? Okey je, semua orang punya okey. Saya suka. Tapi itulah saya tak ada siapa boleh beat Ian lah. Ian punya macam saya mind blown sebab because Ian drew it herself. And you know, because I can't draw, so I wasn't very impressed about that. So it was very cute and Ian lukis sangat comel. So saya sangat suka. Tapi beat semua orang okay. And then saya tengok Farhan punya. Farhan said sneeze is a vector. So I really enjoyed that one. And Jannah said, Jannah punya video was very raw. I really like that. Dia cerita pasal when you're trying to walk on mud and you can change the pressure. I mean, you can prevent yourself from sinking down into the mud if you apply a bigger area. So that was really good. I really like that. It was very spontaneous and very daily life punya situation lah kan. And then Haikal punya about crashing and then kenapa kena pakai seatbelt. Saya dah tengok dah semua. Cuma saya tak sempat komen je lagi. Apa lagi? Amy punya lightning. Ian pendam sesuatu doktor pasal video tu. Apa dia? Pendam apa? Saya dah tengok punya Ian punya juga. Ya Allah. Yang tu sebenarnya ni kan yang saya cakap apa jadi kalau kita terjun bangunan kan. Tapi korang pakai act kan. Pakai juga ni. Apa yang pendam sesuatu tu? Husnia? Kenapa Husnia tak nak jawab? Molly punya. Molly punya tu kan vibration. Apa gitar dia. And I think Molly was wearing something traditional. Was it Molly? Come on. Apa yang Ian pendamkan? Come on, spill the tea. Apa tu? Baju cosplay. Oh my god. Saya ingatkan baju tradisional. Saya macam kenapa? Unik sangat baju Molly ni. Saya tak tengok Demon Slayer tu. I didn't watch Demon Slayer. Baik tak saya ingat baju tradisional? Saya punyalah macam wah semangatnya Molly tunjuk tradisional. Awal saya kena con. Aduh lah. Best ke Demon Slayer? Saya tak pernah tengok lagi. Saya tengok Naruto pun saya dah menangis lah. Saya takut lah nak tengok anime lain. Lepas tu cerita. Okay, so dah 8:30 ke? Oh dah lebih masa dah. Okay. So what is Ian hiding from me? Squid Game. Diorang cakap Squid Game ni kan gruesome kan? Kan? Is it gruesome? Banyak macam darah-darahan, kepotong-potong ke? Tak se-gruesome Voice. Oh Voice pun saya tak tahu. Tapi saya takut tengok cerita yang potong-potong ni. Cuma mass killing. Okay. Saya suka tengok benda yang cute-cute je macam yang lukis tu. Hati tak kental. Okay. Banyak gore tu lah. Saya kurang lah cerita gore ni. Kalau psycho thriller saya suka lah. Tale of the Nine Tail. Naruto ke? Okay Amy. Okay. Okay, so let's continue with our example. Okay, so find the amount of potential energy of an object if its mass is 5 kilogram at position 150 centimeter from the ground. Now remember that we have to declare our ground as h equals to 0. So if it is at a position of 150 centimeter from the ground, it becomes 150 je lah. Oh, kenapa saya punya video kat sini? Okay, so it becomes 150 centimeter, and this is where our object is. We don't know what the object is. So it's asking for the potential energies, not the change in energy, just the potential. So now it becomes U equals to mgh, and they substitute that 5 kilogram, 10.81, and 1.5. So the energy of this object when it is at a height of 150 centimeter above the ground, it is 73.58 joules. And then an object of mass 5 kilogram is moved from A to C. This is point A, and this is point C, by a force of 40 Newton as shown in figure. Find the work done by the force. Okay, so it's moved from A to C, and then by a force of, dia naik ke atas lah, dia start dari sini. So dia naik ke atas, the force applied is 40 Newton ataupun the pulling force ataupun the pushing force. Find the work done by the force. So we know that we need to have a force that is parallel to your displacement. So in this case, our displacement is this way. This angle. Tak salah kan? Tadi saya dengar ada orang cakap. Okay, tak ada. Okay, so our displacement is from A to C. This is our displacement. We need a force that is parallel to that. Assuming there is no friction and any other forces acting parallel to the displacement, we are going to assume that the 40 is our only force. So this is called the isolated system lah. Tak ada benda lain kacau dia. So 40 times 0.05. Remember, you have to use SI unit. So kena convert jadi meter. 40 times 0.05, it becomes 2 Newton. So the work done by this force to move the object by 5 centimeter is 2 Newton. And then calculate the potential energy of the object. So from A to C, it moves by 5 centimeter. However, when we are talking about potential energy, we need to know its vertical displacement. We need to know its vertical displacement. I'm not interested in this parallel displacement because we want to know about its height. Potential energy is about height. So this height is 4. When it goes from A to C, it increases h by 4 centimeters. So positive 4. So UG is equal to mgh. M is 5 kilogram, 9.81. Then our height is 4 centimeter ataupun 0.04 becomes this guy. Remember, mgh kena pakai height. Do not pakai 5 cm ni. Do not pakai the incline punya distance ni. You always have to find this guy. If you have the angle here, 30 degrees, and you have 5 cm, you can find out what is the height if they didn't give this to you. So sine theta equals to opposite over hypotenuse. So if this guy is 30, so it becomes sine 30. Opposite is, we don't know, we're trying to find that. Hypotenuse is 5. You put in this value, you get the height. So don't become clueless lah kalau tengok ada 5 dengan angle je, but there's no height. You can find it yourself using trick lah, trigonometry. Okay, and then a spring is stretched from 12 to 14. Find the amount of energy stored in the spring given that the constant is 100. Spring constant is 150. Why am I not able to talk? 150 Newton per meter. So the extension is 14 minus 12. So we are assuming that this is our original size of the spring. So spring ni mula-mula di 12 centimeter, and then it was stretched, and then it became 14. So the stretching is 2 centimeters. So this is our x. So the extension is 2 ataupun 0.02. So you use this equation 1 over 2 kx squared Just plug in the values. Do not forget this square sign and use it. Okay. So that is your example. Okay, next example. We have time. So a crate of mass 10 kilogram. Saya besarkan dulu. Nanti kita kecilkan balik. So a crate of mass 10 kilogram is pulled up a rough incline. Pulled up. Ditarik ke atas. So if I were to draw this. Okay. It's pulled up a rough incline. We know that we will have friction with an initial speed of 1.5. The pulling force, so it is pulled, and this pulling force FP, FP is equal to 100 Newton parallel to the incline. Oh, why is this so huge? So this is our imaginary axis. Okay, I should have put the axis on the box. Okay, so we have 100 Newton. Our U is 1.5. Let me write everything here. Friction tak tahu. And which makes an angle of 20 degrees with the horizontal. Okay, the coefficient of kinetic friction is 0.4. So it's giving us that value. So we put it there. 0.4 equation for friction is mu r. We have the value for mu. So I'm going to assume this is unknown r there. So the crate is pulled by 5 centimeter. Kan baru cakap tadi, 5 centimeter is the distance that is the crate that is being pulled. Sorry, the distance that the crate travels when it is being pulled is 5 centimeters. So that is your displacement x. Why is my arrow like that? Okay, so that is the motion. FP is this way. How much work is done by the 100 Newton force? So this is easy because we already know that the 100 Newton force ataupun FP is parallel to our delta x. It's parallel to our motion. So that is, we don't have to use the cosine equation anymore. So for A, work done W by FP, work done by the pulling force is equal to FP dot with delta x. But in this case, we already know it's parallel and in the same direction, therefore the angle becomes cosine 0. So if I want to write that, I can, but I'm usually lazy, so I just ignore it. So this becomes 1, then delta x. So it just becomes FP delta x. So FP is 100 and then times with 0.05. So that becomes something. And then for B, how much work is done by gravity? So we know that this is our motion, displacement, gravity kita kat sini. Oops. This is our mg. So this becomes, I need a different color. So this becomes mg cosine theta. And this becomes mg sine theta. We know this is chapter 3. So if we want to talk about the force of gravity that is working, that is doing work on this object, it is opposite direction. Mg is to the left and our displacement is to the right. I should get rid of this. Our displacement is to the right. Therefore, the angle between them is 180. So writing that down. So P over here, work done by gravitational force, Fg. So this is Fg that is parallel to delta x. But in this case, the only component that is parallel to this guy is mg sine theta. So if you didn't want to start with this equation, boleh, it is acceptable. So if you don't want to start with that, so you just say the force that is parallel to delta x. Boleh juga macam ni. Mg sine theta. But in this case, it's a minus, right? It's a minus delta x. You can write it like this, or you can write it like this. F mg sine theta. This is the force that is parallel to our displacement, cosine cosine 180, because you measured the angle between these two guys, mg sine theta and delta x, 180, cosine 180, delta x. Boleh juga tulis macam ni, -1. This is still the same answer. What else? What are the forms of equation that we can write here? F, yeah, I think that's about it. Ada lagi lah, kalau ada yang sama boleh je, pakai je. Asalkan jawapan dia, you know that it's right. And it makes sense and logic. Okay, so that is work done by gravity. So kita plug in the values. M is 10, 9.81, and this is sine of 20. This is mg, this is our theta, mg cosine theta, this is mg sine theta. And then this is 0.05. Now, why didn't we use the height here? Why did we use 5? Can anyone tell me? Why did we use 5 centimeter instead of the height? Boleh ke kalau saya nak pakai height? Come on guys. No one wants to try? Okay, so sebenarnya the displacement of this guy is 5 centimeter here. And if it is 5 centimeter, if we are talking about the 5 centimeter, the force that is acting in that direction is mg sine theta. But if we are talking about the height that increases when this guy goes from here to here, and we can find it, which is 4, right? 4 centimeter. We need to use a force that is parallel to the height, which is mg. So let's see if it's going to give us the same answer. So mg sine theta times 0.05, this needs to have a negative here. So let's see, 10 times 9.81 times sine 20 times 0.05, that will give me 1.68 Newton, joules. Okay, so let's see. Mg is 10 times 9.81 times with 4. Saya tekan dulu. 10 times 9.81 times with 0.04. Tak sama. Kejap. Something wrong here. Dia kena sama. What am I missing here?
Doktor.
Oh, it's 100. Apa dia? Sorry? Yes?
The displacement is 5 meter, not centimeter.
Oh. Benda-benda je saya. 5 meter. Okay. 5 meter. What else? Apa ada lagi tak yang saya silap? Oh, kat sini pun salah. 5 meter. Oh, betul. 5 meter. 100%. So this becomes 500 joules. And this is mg sine theta, force times displacement. 10 times 9.81 times sine 20 times 5. So dia patut sama, dia tak sama. 10.81. 67.76 Newton, joules. Tak sama. Kejap mg times 4. It should be the same. What am I missing here? Mg 10 times 9.1 times 4. Okay, sepatutnya sama. I'm missing something. I need to check back on this one. So abaikan ni dulu. Saya tak boleh cerita lagi pasal ni. Kenapa saya punya value tak sama? Okay, never mind. Nanti saya akan cerita balik. Saya akan refer back to the textbook if I'm doing any mistakes. So how much work is done by gravity? We already solved that. So we took the mg sine theta times with 5 meter because this is our displacement. How much mechanical energy is lost due to friction? Okay, how much energy is lost due to friction? So that is our C. So we need to know our R in order for us to know what is our F. In this case, our box is not flying, so we can say that Fy is equal, net into Fy is equal to 0, and this is going to be equal to R minus mg cosine theta. And therefore, R is mg cosine theta, m is 10, 9.81, and sine 20 times 1. This is 1.71. Kamu saya letak 4, saya betul tahu lah. Betul ke? Sekejap. Sine 20, opposite of hypotenuse, times 1.71. 1.71, kejap Sorry, times 10, times 9.1. Okay, sama. Okay, saya cerita balik. Kalau lagi 10 minit je, okay, kejap dulu. So R equals to 10 times 9.81 cosine 20. So that is going to be 10 times 9.81 times cosine 20, which is 92.18. Okay, so that is your reaction force. We needed to find for friction. So friction is times 0.4. So you get 36.87. So it's asking how much mechanical energy is lost due to friction. So we are actually calculating for non-conservative work, which is 36.87. Friction is this way. I need to write it down. Patutnya kita start free body diagram, tapi saya tak tahu kenapa saya tak buat. Free body friction is that way, and our motion is the opposite way, so it's going to have a negative. Opposite direction of force and displacement will give you a negative work done. Ataupun kalau tak nak ingat macam tu, nak letak cosine 180, boleh. So it's going to be negative 36.87 times with 5. So that is the work done ataupun energy lost by friction. So 36.87 times with 5. So you get 184.35 joules. So you are losing this much negative. You are losing this much from your system. Where does it go? It becomes heat. It becomes kadang-kadang it becomes kalau kita bergeser kan, kadang-kadang dia jadi heat, kadang-kadang dia rosakkan permukaan. So benda-benda tu datang daripada energy. It does not come out of nowhere. We are actually losing energy when we have friction, and that energy is converted to heat, vibration, or like damage to the object, stuff like that. So this is where it goes. What is the total work done on the crate? So now we just add all these things together. So W total, kita dah buat A, B, C, walaupun huru hara. So this is G, work total, tambah je lah 500, and then 167, this is a minus, and then this guy is also a minus. So work total is 500. What's wrong with my, okay, 500 minus 167.7. Kenapa minus? Sebab dia terbalik. Mg sin theta times displacement terbalik, negative work. And then friction also is negative work. So that becomes 184.35. So this answer is minus 167.76 minus 184.35. So that is 147.89. Kenapa saya pakai warna ni? Joules. So that is your answer. What is the speed of the crate after being pulled 5 meter? So we have the work done. We know that work done is the change in energy. Can I use the work energy theorem here? Boleh tak? Okay, remember work done is the change in energy. They're asking us what is the speed of the crate after being pulled 5 meter. Maksudnya the final V. We started with U of 1.5. Where's the slide? Okay, I want to duplicate. Okay, so jawapannya boleh kita boleh pakai kita boleh pakai the work energy theorem, or if you want to use the conservation of energy punya equation pun boleh. So those are two different things. So if we wanted to use the work energy theorem, so it becomes W equals to the change in KE. Boleh So W equals to the change in KE. So this one, we already know that our W was, total work done was 147.89. Okay, so that is equal to 1 over 2, M is 10, and then we have V squared minus U squared, which is 1.5. So 147.89 times 2 divided by 10, and then plus with 1.5 squared, and then square root that answer, you would get V as 5.64 meter per second. So the speed is increasing because we are applying force to pull it. So speed increase, which makes sense. And the friction is not bigger than our pulling force. Mg sine theta is also not bigger than our pulling force. So therefore, we have acceleration on the right hand, on the up the incline. So we are increasing in velocity. Now, I wanted to talk to you about when we have work done. Yeah, I can't do this one. I told you guys, if we wanted to find out how much work is done by gravity, specifically this question, how much work is done by gravity? So why are we not using this mg instead of, why are we not using mg lah? Kenapa kita nak pakai mg sin theta juga? The answer, the easy answer for that is because our motion is this way. We already know the value, which is 5. So we want to use something that we know. But what if we know that the height increase is 1.71? Can I use mg instead? The answer is yes. Because macam mana saya dapat 1.71 ni? Sin 20 equals to opposite over hypotenuse, which is 5. So this becomes 5. Sin 20 times 5, you get your opposite side as 1.71. So if they ask you how much work is done by gravity, you can actually use mg ni kalau nak. So your answer would be work done equals to mg dot with height, but in this case height kita adalah 1.71. So if I expand this equation, alah susahnya. Okay, so W equals to mg dot with h. I expand this, it becomes mg cosine 180h. Kenapa 180? Mg is going down, height. The height of this guy is going up. Dia naik atas, dia naik incline. The height increases by 1.71. And our force is acting downwards. So this becomes 1 minus 1. Yeah. Minus 1. So this is mg 10 times 9.81 times 1.71. Your answer will be 1.71, 167.75 minus. So sama. So you can use either one. You can use the mg sin theta times 5, or you can use mg times 1.71. Dua-dua akan give a minus answer. Dua-dua will give you the same magnitude. The only difference is how you determine the displacement. Do you want to determine it in the parallel axis, or do you want to go for its height? You can go for either one, whichever that you like. Okay, so that is it for today. Nanti kita akan sambung with more problems later on. Harder problems. This is quite easy sebenarnya. So please continue doing your chapter 3 punya web assign, and I will see you next week. Bye-bye guys. Take care and have a great rest of the day.
Thank you, Doctor.
Welcome. Bye-bye.
Thank you, Doctor.
Thank you, Doctor.
Bye-bye.
Thank you, Doctor.
Welcome. Bye.